In the activity, you guys were looking at momentum, and we learned the physics definition of momentum. It's a little bit different than our everyday usage, but it's sort of got some similarities. Momentum is mass times velocity, and since our typical units of these are kilograms and meters per second, what we have is the unit of momentum is actually a kilogram meter per second. And that doesn't have a special name, like a Newton is a kilogram meter per second per second. This is just a kilogram meter per second. It doesn't have a special name. So when we're talking momentum, that'll be the unit we use. But because it does depend on mass and velocity, there's a couple interesting things that happen. First, it doesn't matter how much mass something has. If its velocity is 0, if it's at rest, it has no momentum. So an elephant standing still has less momentum than a mouse running across the ground because the elephant's not moving. The other thing that happens is velocity is a vector. So velocity actually has a direction. If we had two carts, and one cart is moving this way, and the other cart is moving this way, they have equal masses, say 2 kilograms, and they're moving at the same speed, say 4 meters per second, then do they actually have the same velocity? That's what I wrote. It said v equals 4 meters per second. But if this one's moving this way and this one's moving this way, then we have to remember that they don't actually have the same velocity. Yes, they have the same speed, 4 meters per second, but this one has a velocity of positive 4 meters per second, and this one has a velocity of negative 4 meters per second. And that negative tells us about a direction. But that means this one's momentum over here is 2 times 4, or 8 kilogram meters per second, and this one's momentum is 2 times negative 4, which is negative 8 meters per second times kilograms. Okay? Now, what's interesting about that is if we add up those two momentums, they would sum up to 0. So I could say the total momentum on this thing is 8 plus a negative 8, which equals 0 kilogram meters per second. Even though they don't have 0 energy, right? Because energy is 1/2 mv squared for kinetic energy. This negative is actually going to get squared out of the equation. So we'd have 1/2 2 times 4 squared plus 1/2 2 times negative 4 squared. And together these things actually have 16 plus 16 equals 32 joules of kinetic energy. So even though their momentum sums to 0, their kinetic energy doesn't. So because momentum is a vector, sometimes we have to pay attention to direction and what's going on with that. And that's especially important when we think about collisions, because what we have is Newton's second law, which says net force equals mass times acceleration. But remember, acceleration is merely the rate of change of velocity, change in velocity over time. Remember, that's v minus v naught divided by t. If we go ahead and we make this substitution into Newton's second law, then what we get is m times v minus v naught over t is equal to the net force acting on an object. Well, that means net force is equal to mv minus mv naught, and this is over time. Well, that is momentum. This is initial momentum. So that tells us the net force acting on an object is equal to its change in momentum divided by time, which actually is a little bit counterintuitive, at least at first. If you think of like a target, something sitting up here, and it's fairly heavy, and you're going to throw a ball at it to try to knock it off this wall and have it fall over. Then you have two options. You have a baseball or a rigid ball that is going, let's go with a ball made out of clay. Clay ball hits that and it sticks. Okay? Or you could throw an almost identical ball except that it's a bouncy ball and it hits that and bounces back. Which one of those do you think would have a better chance of knocking this heavy thing off of the shelf? Well, if we think about that, we're like, well, the clay ball hits it and sticks. It's going to transfer all its energy to it. It's going to cause a bigger change. But if we look at what this says, we're going to be a little bit surprised, I think, because net force is change in momentum over time. A bouncy ball, like let's say it's initially moving this way and then it bounces back. That means when we find its change in momentum, we have an initial negative momentum. Okay, so let's see. Its initial momentum is some kind of negative value, negative p1. Okay? Its final momentum is actually, now that it's bouncing back the other way, is some positive value, say p2. And so what we get is a change in momentum, delta p, is equal to final minus initial P2 minus a minus P1. Okay? And that's actually equal to P1 plus P2. So we have to sum up two momenta to figure out how much it changed. Whereas a ball that actually just bounces or doesn't bounce back but sticks, its change in momentum, well, it has an initial momentum of, say, negative P1, and its final momentum is 0. So when we do this, we have 0 minus a negative P1, and that just gets us P1. There is no added thing to it. So that means it has less of a change in momentum. And assuming that it takes the same amount of time for a clay ball to squish and stop as it does for a bouncy ball to bounce off of a surface, that means the bouncy ball actually has a greater force exerted on it. And Newton's third law, remember, tells us that every action has an equal and opposite reaction. So if we take a little bit closer look at that, right, here's right during the collision these two things hit. Well, there's two forces that act. There's the force on this ball, right? This is the force back, and that's from this thing, okay? Whatever it is, from object. So this ball that we throw at the object is going to actually exert a force on this ball and stop it. But there's a second force, according to Newton's second law, that acts on this ball, right? And this is the force on the object from the ball. And according to Newton's third law, those two forces are equal and opposite. So if this force is bigger because it bounces back instead of just stops, then this force is also bigger, and therefore the ball that bounces is going to have a greater change or affect this massive object a little bit more.